Welcome friends, Igor is here, and in this video we will define and study non-singular matrices. In this lesson we will define non-singular matrices, learn how to check if a matrix is non-singular, and prove that a matrix is non-singular if and only if its reduced row echelon form is the identity matrix. Let's get started. The notion of a non-singular matrix is crucial for linear algebra. It is one of the central notions, and we will use it throughout the rest of the course. We start by defining square matrices. A matrix is square if the number of rows is equal to the number of columns. When we have a square n by n matrix, we will say that it has size n. Sometimes we will have to emphasize that we are working with the matrix which is not square. In this case, we will call such matrix rectangular. And now we are ready to define non-singular matrices. First of all, this notion applies only to square matrices. A square matrix is called a non-singular matrix if the homogeneous linear system with this matrix as the coefficient matrix has only the trivial solution. Otherwise, the square matrix is a singular matrix. To check if a square matrix is non-singular, we need to construct a homogeneous linear system with this matrix as the coefficient matrix, solve that homogeneous linear system, and look at the solution set. We have an algorithm that solves any linear system, and therefore we can decide whether any given matrix is non-singular, and the process of this determination involves solving a homogeneous linear system. Please be careful in applying proper terminology. For example, it makes no sense to call a linear system non-singular because this term applies only to matrices. Also, you cannot call a rectangular matrix singular because the terms singular and non-singular apply only to square matrices. Let's consider a square matrix of size 3. We need to decide if this matrix is singular or non-singular. For this, we are going to construct a homogeneous linear system with this matrix as the coefficient matrix. Now, we need to solve this system. So, we construct the augmented matrix of this system, and we find the reduced row echelon form of this matrix. It is now easy to read the solution set from the reduced row echelon form matrix. For example, we see that x3 is a free variable and there are infinitely many solutions. According to our definition, this means the matrix is singular. Let's look at another example of a square matrix of size 3. We also construct the corresponding homogeneous linear system, we look at the augmented matrix, we reduce the augmented matrix, and now we see that this linear system has only the trivial solution. By our definition, this means the matrix is a non-singular matrix. Next, let's define a very special kind of a square matrix called the identity matrix. This matrix is defined as follows. Its entries are either 1 or 0, and the entry is equal to 1 if the row index is equal to the column index. The entry is equal to 0 otherwise. Here is a visual example of a square matrix of size 4. As you see, it has 1s in the positions 1, 1, 2, 2, 3, 3, and 4, 4. These positions comprise the main diagonal of a square matrix. The reason why this matrix is called the identity matrix will become clear later when we define matrix multiplication. Let me just give you a little teaser. This matrix will have the same property as number 1 with respect to matrix multiplication. Now, let's establish a criterion for non-singularity of a square matrix. A square matrix is non-singular if and only if its reduced row echelon form is the identity matrix. Of course, we pay careful attention to the if and only if formulation, and it means that there are two separate implications for us to prove. First, we need to prove if a square matrix is non-singular, then its reduced row echelon form is the identity matrix, and then conversely, if the reduced row echelon form of a square matrix is the identity matrix, then that matrix is non-singular. Let's denote by A the original square matrix and by B its reduced row echelon form. In one direction, we are going to assume that B is the identity matrix, and we need to prove that this forces A to be a non-singular matrix. To decide if A is a non-singular matrix, we need to solve the homogeneous linear system with A as the coefficient matrix. To do this, we form the augmented matrix of this system, which contains matrix A as the coefficient matrix with the extra column of constants. In this case, it's the zero vector. But now, let's think what happens when we row reduce this augmented matrix. You should have done some computations of solutions of homogeneous linear systems, and by now you have observed that whenever you apply row operations, the last column, the zero column, never changes. And this means that when you reduce such an augmented matrix, the actual non-trivial reduction only happens within the matrix A, the coefficient matrix. But we already know that the reduced row echelon form of A is the matrix B. Therefore, when you reduce the augmented matrix of the homogeneous linear system, the reduced matrix, the reduced row echelon form of this augmented matrix, is the matrix which consists of the matrix B with the zero vector added as an extra column. Also, our assumption was that B is the identity matrix. This means that when we reduce the augmented matrix of the homogeneous linear system with A as the coefficient matrix, what we will get is the identity matrix plus the zero vector. If you recall what an identity matrix looks like, you will realize that every column of the identity matrix is a pivot column. This means every variable is a dependent variable, and therefore the system has a unique solution. Because it is a homogeneous linear system, this unique solution must be the trivial solution. This is exactly what it means for the matrix A to be non-singular. In the other direction, we are going to assume that A is a non-singular matrix, and we need to prove that its reduced row echelon form is the identity matrix. Since A is non-singular, by the definition of a non-singular matrix, it means that the corresponding homogeneous linear system has only the trivial solution. And because we have a unique solution, it means we do not have any free variables. Every variable is a dependent variable. In turn, this means that every column in the reduced form of the coefficient matrix is a pivot column. So, we have a square matrix where every column is a pivot column. The only way for this to happen is for this matrix to be the identity matrix. Let me illustrate why this result is useful. Let's look at the following 3x3 matrix. Previously, to decide if such a matrix is a non-singular matrix, we had to construct a homogeneous linear system and its augmented matrix. Effectively, we took the original matrix A and added an extra column. But now, we are not going to construct the augmented matrix. We are not going to add this extra zero vector as the last column of the matrix. Instead, we are going to reduce the original matrix. We see that its reduced row echelon form is not the identity matrix, and therefore the original matrix A is a singular matrix. So, in fact, you do not need to construct homogeneous linear systems. You can simply reduce the matrix itself and look at the resulting reduced row echelon form to decide if the matrix is singular or non-singular. If you found this video useful, please like and subscribe to help others discover this content. In the next video in this series, we will discover some additional properties of non-singular matrices. I will see you later.